Okay, you guys have done a whole bunch of work with theories of light. You can look at particle model. You guys have looked at wave model. You guys have looked at some major experiments with Young and Snell and Huygens principle and a whole bunch of other stuff as well. And let's sort of tie a few things together. I posted a sheet on your class website that's really going to come in handy for this, so you can sort of fill things in as we go along and see if we can summarize the theories and piece a few things together. Now, the first main theory you guys looked at, of course, was the particle theory. And of course, this was developed by Newton. He could explain so many things of what light does and how light works when he treated it as a bullet. Now, of course, he couldn't really explain partial reflection that well and a few other things, but it was really, really, really good. Then you guys got into the wave theory, and the wave theory is shown by both Huygens principle and Young to be true, that there's definitely a wave nature to light, which explains the interference pattern from the Young experiment, explains the polarization film thing I showed you guys. There's lots of different things that it explains. So we got to try and put these together yet, but we're a little more details with the wave theory first. It's generally accepted to be a combination of electric fields and magnetic fields. And this takes care of one of the major problems that the wave theory had, because the wave theory of light cannot explain how light traveled through a vacuum, like empty space. The particle model could. The bullet model, bullets can travel through empty space, no problem. But the wave theory, one of the big problems they had is they could not explain how light travels through a vacuum. But electric fields and magnetic fields go through vacuums all the time. And through ways they sort of figured out that you'll learn more in grade 12, they figured out as a combination of electric fields and magnetic fields, because these guys do not require a medium to travel, and that's where the term electromagnetic wave comes from. So you got the particle model by Newton replaced by the wave model in especially early mid-1800s, shown to definitely be more accurate for a lot of things, and the electromagnetic wave idea comes along. Then somebody else comes into the mixture. Then Einstein comes into the story. And Einstein comes along to try and explain something that's actually been observed by a few people before, but they didn't really research it, and he tried to explain it. And Einstein comes along, and he tries to explain why certain metals exposed to ultraviolet light would emit electrons. You'd have higher current flows, sparks, different things would actually happen. So this is where the term photon really kicks in. You guys may have heard of photons before, where you got this photon of light coming in, hitting a piece of metal, and electrons would come off. Now, the dominant theory of light at the time is the wave theory. So the wave theory of light comes in to explain it. And the wave theory says that energy builds up in the metal, because, of course, waves carry energy, and when the electron has enough energy, it will jump off. Now, of course, you don't see this all the time, and that's because they figured most light, like sunlight, the energy is too low. But if you could wait long enough, then electrons would start jumping. So like metal in sunshine would start sparking and stuff like that, or might give you a little zap or something like that. But basically, the sun just sets before it can absorb enough energy, and thus you don't get it. But the idea was, the wave theory says energy builds up in the metal until the electrons build up enough energy and they jump off. So if the low energy light is actually used, first of all, you can just wait. You just have to wait and it'll build up the energy and eventually something will happen. Or if you want, just make the light brighter, because if you make the light brighter, more energy is coming in. That's called the intensity, and then it would work. So Einstein was working with this and trying to figure it out. And the thing is, both of these ideas actually failed. It didn't matter how bright he made the light. It didn't matter how long the light was on. Nothing ever happened. Both of these ideas failed miserably. The wave theory of light could not explain the electrons moving when light was hitting it. It had no explanation whatsoever. So Einstein actually then applied the idea for somebody else that you guys will also learn about in grade 12 to figure out how this worked. So Einstein said that the electrons were actually being knocked off or shot off by a bundle of energy called a photon. That's the term photon kicks in the diagram. But that's a particle idea, which of course probably pissed off a lot of people who thought that light traveled as a wave and a wave theory can explain it. So we brought back a particle idea, which really threw people off. And basically he said if the light frequency is too low, and this was called threshold frequency, there's not enough energy and the photon is too weak to release the electron. So he actually used an idea that, again, you guys will learn in grade 12, that frequency is directly connected to how much energy a photon actually has. And if the photon is too weak, it can't move the electron. It doesn't matter how often you use it, how long you wait, or how bright it is. It doesn't make any difference. It's just too weak. Okay, so it's sort of like shooting a Nerf gun at the side of a car. If you shoot a Nerf gun at the side of the car, it's not going to punch a hole through the side of the car. The bullet's too weak. It doesn't matter how long you press the Nerf gun bullet against the side of the car. It doesn't matter how many bullets you use. It doesn't matter how long you wait. It'll never happen. You have to get a high-powered gun with a bullet fast enough and strong enough to actually make it through. So he said that if it's below this threshold frequency or threshold energy, the photon's too weak, nothing is going to happen. It doesn't matter how long you wait or how intense it is, it makes no difference. But if you reach this threshold frequency, if you reach this threshold energy, then something can happen. Okay? So if you go past that threshold frequency, electrons will actually start coming off faster. There's more energy and they come shooting off even faster. And the more intense the light is, you get more electrons. And the actual electron comes up right after it gets hit by the light. There's no wait time. There's no waiting for anything to happen, where the wave model says you just have to wait and it'll come. No, like there's no wait time. It happened right away. If you shoot the side of a car with a gun, you don't have to wait for the hole to show up. It's not going to happen. It's going to happen right away. And either it's going to work or it's not going to work. So he figured out how this all pieces together. Now, this is what is called the photoelectric effect, and it's what he won his Nobel Prize for in 1921. And you guys use the photoelectric effect all the time. This is how solar-powered calculators work and solar-powered stuff. With anything with a little solar panel that uses light to make electricity, that's how it works. So those little solar panels in your calculators and toys and whatever else, that's a 100-year-old idea from Einstein. Okay? So it was definite proof and evidence that there's still a particle component to how light works. So we've got two conflicting theories and conflicting ideas. We've got the Young experiment and Snell's law and all that kind of stuff proving that light travels as a wave, and even polarization films show that. But then you got stuff like the photoelectric effect, and there's other effects as well that you learn about in grade 12, I'll show that to you as well, that show that light has to travel also as a particle. So which one is it? Is it a particle or is it a wave? Well, there's the problem right there. You can't pick one or the other. So it is currently seen as a combination of both theories. And that's one of the mistakes people made for hundreds and hundreds of years. They thought it had to be one or the other. Why can't it be both? Okay. So the great way to think about it, the way I like to think about it, is you have this electromagnetic wave, this EM wave, and this EM wave acts as a guiding path for an energy bundle. So the energy bundle is that photon, that packet of energy, that little particle thing. And that's how you can have both. So if you're working with Snell's law or the Young experiment, well, then you're working with the guiding path. You're sort of fooling around with that part of the light. But if you are working with the photoelectric effect and other stuff that you guys will take a little bit later on, that is when you're focusing on the energy part. So it's actually like a combination of the two. Okay, so you can choose to look at it one way or the other way. You can work with the wave part. You can work with the bundle part. But the two always exist together. And since it can be both, this is where the term duality kicks in. So you have this bundle of energy called the photon riding this electromagnetic wave pathway. So you can interact with either or whatever part you want. And this is where the term duality kicks in. So it's both things simultaneously, but you sort of have to pick which one you want to work with. And again, you can take this in more detail in grade 12. I'll show you some really cool stuff with this. And this duality particle wave idea leads to some really, really amazing, cool stuff in physics and chemistry and a whole bunch of other stuff that you never think would actually be possible. It's really, really neat. But that's the big thing with light. It's not a particle or a wave. It's sort of both at the same time, and you sort of interact with it as either one or the other, depending on how you want to look at it. It's sort of like a mother. Okay, a mother is both a mother, but she's also a daughter, right? Like she also has a mom and a dad. So you can either interact with it, like her children would interact with her as a mom, but her parents, the grandparents, would act with her like a daughter. So she's both a mother and a daughter, but you can interact with her depending on how you want to look at it, and depending on who you are, you can choose to interact with her as either a mother or a daughter, even though she's actually a combination of both. And that's sort of like an idea of how duality works. Okay, but again, in grade 12, we will take this in a lot more detail. And with this is where we come to the end of what we like to look at in terms of light in grade 11 physics. And we can expand on some more of the really, really cool parts of this in grade 12.